the normal density is patently positive everywhere as a function. Is it properly normalized? And to check its bona fides, we have to look at the area under the curve. So remember, phi of x was e to the minus x squared over 2 divided by the square root of 2 pi. I want to integrate this and see if I get 1. The student might want to pause and see if she could play with it. I mean, this looks promising. I mean, you've done exponential integrals before. This looks like something that, with a little bit of tweaking, should get you there. If you're curious, pause and try it out. Now that you come back, you'll have realized that if you tweak it, the usual substitutions just don't seem to work. You keep getting things which are not quite right. The fastest way through this is to rely unabashedly on a trick. It's a simple trick, but it is not at all obvious that this particular trick is going to work without a lot of experience with the normal distribution. So, here's the trick. If this integral is to be 1, then squaring it is 1 squared, and that should also be 1. Right? The integral is clearly positive. So if I look at the square of the integral, and I can show the square is unit, then the integral itself must be 1. So here's a very simple idea. It sounds like a crazy idea, right? But humor me. Right? Square the integral. Now, if you square it, then what are you doing? You're taking the integral and multiplying it by itself. Right? An identical copy. But I don't want to mix up the variables, right? So you have variables of integration. These are dummy variables. Right? So let's call the dummy variable of integration for the first integral x, and let's call the dummy variable of integration for the second integral, naturally, y. Of course, these are copies of each other. Okay. So now we've got two integrals side by side. This is not already looking promising. It looks a lot worse than the integral we started with. But again, bear with me. Let's assemble these integrals together. There are two square root of 2 pi's in the denominator. Multiply them, you get a 2 pi. Pull them out of the integral. They don't depend on x or y. And then you have two exponential functions. If you multiply two exponential functions, then by the usual rule of exponents, the exponents will add. And therefore, this pair of integrals is the same as 1 over 2 pi times a double integral of an exponential function with exponent minus 1/2 of x squared plus y squared. dy dx. And you look at me and says, the man's gone stark staring mad. A single integral is bad enough, and now he's given us a double integral. Let's pause. Something clever has happened here. Take a look at the integrand, in particular the exponent. It's x squared plus y squared. Does that ring a bell? Does that remind you of something? Maybe an atavistic tug at memory. Maybe you're reminded of a rectangular to polar coordinate conversion. If you look at a rectangular to polar transformation, then you replace the coordinate x by r times cosine of theta. R is a radial parameter, theta is an angular parameter. Y then will be r times sine of theta. Then you find that r squared is exactly x squared plus y squared. And now here's where the circle comes in. That is the radius squared of a circle. Excellent. And dy dx becomes r dr d theta. And therefore, by going to a polar system, we obtain 1 over 2 pi outside the integral. The integral over r runs from radius 0 to radius infinite. The inner integral over theta runs over all angles from 0 to 2 pi. The integrand, well, x squared plus y squared is exactly r squared. It becomes e to the minus r squared over 2. And dy dx becomes r d theta dr. We made progress here. Because in the double integral, we find a portion of the integrand doesn't depend upon theta. It can come out of the inner integral. And therefore, we get an outer integral over r and an inner integral from 0 to 2 pi of d theta. Of course, the integral from 0 to 2 pi of d theta is just 2 pi. And therefore, we get now a single integral multiplied by 2 pi. We strike out 2 pi in the numerator and in the denominator, and that leaves us a single integral to evaluate. Superficially, it looks like the integral we started with, but with one critical difference. There is a term r in front of the dr. And this immediately suggests that perhaps a standard change of variable might work, and indeed it does. Suppose we replace r squared over 2 by a variable of integration t. Then dt becomes r dr, and with this change of variable, our integral collapses into the form, an integral from 0 to infinity, of a decaying exponential function e to the minus t. Of course, this is a completely standard exponential integral, and we simply write the answer down. We get 1 minus 0, or 1, indeed, as it must. So in fact, the normal density is indeed properly normalized, and this analysis has shown us also something about the origins of that mysterious square root of 2 pi in the denominator. It arises because of a certain circular symmetry that is inherent in the normal. Okay, but I'm getting ahead of myself.